Okay, so we were just finishing up this problem that we stopped earlier. I think I can go ahead and simplify that a little bit before we invert the transform. That's 1 half times 1 over s minus 1 half times s minus 1 over s minus 1 squared plus 1. Then we have the minus times the minus would be a plus, so that would be plus 3 halves, right? Times 1 over s minus 1 squared plus 1. Good. And so now we're ready to go ahead and invert the transform. So that'll be 1 half minus 1 half e to the t cosine t plus 3 halves e to the t sine t. Good. So there's our solution. Just to remind you what we were doing, let's see, where were we? I thought we had an extra term up here. We haven't quite finished the problem yet, right? So we got this piece, but of course we still have, oh no, we did put those two together, right? That was that one. Good. So that is the solution to the whole thing. Good. I shouldn't have taken such a big break. Okay, I'm going to pause here and we've got time for a couple more sample problems. Good. So this one, we're just doing a little practice with the convolution theorem. By the way, notice that the convolution is actually defined. Do you remember how to define it? Integral from 0 to t, and then it's either one of these could be f and either one could be g, so we could just make this one f and this one g, so that's like f of u, which is u in this case, and then times we'll shift this one, so that would be e to the t minus u du. Okay, but we don't want to actually compute that. This was just for extra. You could though, right? Because the e to the t is actually constant in this problem, so you could actually factor that out, right? And then you would have a integration by parts problem. But what we want to do instead, though, is we want to use the convolution theorem to compute this. So the idea here is that the Laplace transform of f of t convolved with g of t is f of s times g of s. That's the convolution theorem. And so therefore, if I take the Laplace transform of t convolved with e to the t, I'll get the Laplace transform of t times the Laplace transform of e to the t, which is 1 over s squared times s minus 1. Now notice that we can rewrite that using partial fractions. Oops, plus c. Good. And so we'll solve for a, b, and c real quick. That's going to be a times s minus 1 plus b times s minus 1 plus cs squared. So just to make a note there, minus as plus bs minus b plus cs squared equals 1. Right? So then we get the s squared terms. A plus c equals 0. Then the s terms, minus a plus b, is equal to 0. And then our constants is just minus b. So therefore b is equal to minus 1. A is equal to b, so that's minus 1. And c is equal to positive 1 then. Good. And so then following this along, we get that the Laplace transform of t convolved with e to the t is equal to minus 1 over s plus, minus 1 over s squared plus 1 over s minus 1. Good. And now we can take the inverse Laplace transform of both sides to get that t convolved with e to the t is the inverse transform of this, which is minus 1 minus t plus e to the t. Very good. All right. So that's some good practice there with the convolution. By the way, just as a reminder, when you're solving for DEs, y of t should not be in terms of a convolution unless specifically allowed. By that I mean, if you're coming down here and you're solving a differential equation and you have that y of s is equal to 1 over s squared times s minus 1, then we do not want to see, let me put this in red, we do not want to say y of t is t convolved with e to the t, right? Rather, you want to go into use partial fractions. So that's what I mean. So don't use the convolution as a shortcut for like partial fractions. Good. All right. I'll try to be pretty specific in the instructions. Good. All right. Let me pause while I write down one more. So I think one that we'll do is to find a formula for the Laplace transform of y double prime in terms of the Laplace transform of y. And the idea here is that we don't want to use the table, but we want to using the definition of the Laplace transform. Okay, so how's that going to go? The Laplace transform of y double prime is the integral from 0 to infinity e to the minus st y double prime of t dt. And so if we want to get things in terms of the Laplace transform of y, right, we need to somehow get rid of the derivative there and get the original function. By the way, we're going to call this y of s, right? Good. Okay, so then let's go ahead and I think we can do, if I have y double prime at the end, right, I can anti-differentiate a couple of times in the table for the, do you recognize that? Sine u dv. Okay, and so I would have my plus here and my e to the minus st here, minus s e to the minus st, s squared e to the minus st, minus plus. And so I see that this integral is going to be y prime times e to the minus st from 0 to infinity. Minus minus is a plus, so that's going to be plus s y e to the minus st from 0 to infinity. And then we have plus s squared times the integral from 0 to infinity e to the minus st y of t dt. Good, and so this is your y of s. Good. Now, what has to happen as little t goes to infinity of y prime times e to the minus st? Well, this limit better be 0, otherwise we're going to have trouble if we had to integrate that from 0 to infinity, right? So we're going to go ahead and assume that the limit is 0 because we're assuming that it's of exponential order. Okay, so that for some exponential function you're going to quash the derivative. And then here we'll assume that this limit is 0 as well. So that just leaves us with 0 minus, and then if you plug in 0, you get y prime is 0. And then here we get infinity is going to be 0, so then we have minus s times y of 0. Good, plus s squared times y of s. Alright, so then we have our equation s squared y of s minus sy of 0 minus y prime of 0, which is the formula. Hopefully it looks familiar. Very good. Okay, that's it for the videos. I got a little carried away, but everything should be ready to go now.